No questions? Good to go? Okay, alcohols and ethers. Elimination using paclopyridine. Product here, paclopyridine. Yeah? Dehydration, we can call that the Zaitsev product. The one below, note, this carbon is chiral here, it's tetrahedral. The carbon now is trigonal-planar if we would draw the methyl group plane. Some students will draw this still bolded or dashed. That's sp2 planar now. The one below, anybody? What would this one give? That there? Actually favor the Hoffman product there, yeah?
Can we go over the chair conformation to determine the beta hydrogen?
For what reason? Why do you want to look at chair?
Because that's how we're going to determine which hydrogen. Why wouldn't we take the other hydrogen?
Because it's not anti-planar.
Only one of those H's is going to be anticoplanar to the leaving group. Which one is it? HA. So if you label which H remains over there, HB remains. But H is H. Trans. Thus transcoplanar. Leaving group must be axial. Conformation leaving group must be axial.
Oh, so because HA is trans, then we know automatically it's trans anticoplanar?
Transcoplanar.
We don't have to do a chair conformation? I thought that's what we...
No, you don't have to. You can if you want to clearly see that they're transcoplanar. This hydrogen is cis. It cannot be transcoplanar. It can be ciscoplanar, but transcoplanar is highly preferred when you do a heat elimination. These can only be ciscoplanar. Okay? Boom, there's your leaving group. It's going to be, isn't it the dichlorophosphate? Yeah? Here's an H here, here's an H here. The methyl is trans. That means it's down. Okay, there's your H's. That's C. This is A, and that's B. A and the leaving group, straight up, straight down. This H is, there's the H. There's the leaving group, anticoplanar, HA. It's going to eliminate HA. Boom, double bond there. Methyl remains. HB and AC remains. KOH is gonna make the phenoxide anion, right? Then we throw in this here, we have a good leaving group, tosylate, Carl. We're gonna come in here and we're going to do an SN2, and we're going to get right? We make our bond here. Oxygen now bonded to that carbon instead of the tosylate. And we have an ether, a classical Williamson ether synthesis.
That would
Lawrence?
cause an inversion.
Right, inversion.
It's just, you still drew it as the same, the treatment as a wedge.
No, it's inverted.
It's just because the weights, it goes on, instead of R, it's S now. Instead,
Right, it's inverted. Right?
would it be fine if you just drew it from wedge to dash?
As long as you had it inverted.
Or, okay.
You don't have your one. Just like I told you to draw the right hand on the board, you can draw it like that, or you can draw it like that, or this. Just the right hand. Question?
Are you saying that if the benzene ring were on the other side of the oxygen, would that deuterium be dashed then?
I think so, yeah. Just like if the palm was facing forward, the thumb would have to be on the right. Same type of thing. No, the leaving group, the nucleophile comes in over here, opposite the leaving group. These two groups get inverted from here to there. But the deuterium is still forward. Or you can do R and S. I mean, this is, as long as this is the same priority as this, then it is. That's 1, 2, 3, H in the back. What is this, S? I bet you a steak dinner, that's R. 1, 2, 3. H in the back. R. I prefer T-bone and baked potato. Right? Now we could just show it. You just want to replace the leaving group with the new thing. You have the O and the aromatic ring that was hot. Now then you'd put the deuterium like it. We could show it like that if you wanted, Lawrence.
Yeah, I saw on my work where if I had it the way like still drawn but inverted, it's still the same. So
We could have showed it like this. This is the same thing as I drew over there. Don't fall into the trap of if that's bold, it has to be dashed. Williamson ether synthesis. We can back this up to this oxygen reacting with maybe something like this. Or we could back this up to this oxygen reacting with something like this. That is, we can make this O carbon bond or that O carbon bond. Which one's best?
The bottom one?
Clearly the bottom one. Boom. that will give this product making O carbon bond here. Yes, no. This is no good. Why?
The carbon attached to the bromine is not carbon.
That's not a tetrahedral carbon. That's not going to be SN2 because now we can start answering why here. If this did attack here, which bond are we going to break? The single bond of bromine or the pi bond of carbon?
Bond of carbon.
Yeah, you're going to do something like that. And once you start doing that, you're not doing SN2 because SN2 involves coming in and kicking off the leaving group. And we haven't talked about this yet, but you're not going to do this either, not easily. This requires something else on this ring. You can't do it yet. In fact, you're never going to be able to do it with those exact molecules there. Down below is a nice SN2. And so when we have a choice, we need to make the right decision. Yeah? And then this would just come from phenol, reacting it with like KOH like we did on the previous example, yeah? Why is the Williamson ether synthesis here not logical? Yes, carboxylic acid is more acidic. One equivalent of KOH. We're going to make the anion here. You can do that. This will alkylate. You're going to get the ester here. Okay? Acid-base reaction. This takes the most acidic H. The acid has a pKa of what?
3 to 4.
About 4 to 5. Phenol,
8 to 10.
about 8 to 10. Good. That can be much lower. Trinitrophenol. It has a pKa of about 1. Phenols can vary greatly depending on the substituents. Standard phenol is about 8 to 10. Phenol itself is about 10. Bioethers. Okay, these reactions here. Cleavage reactions. When there's a tertiary site, we're going to do SN1. If no tertiary site, we're going to do SN2. Up top, we did an SN1. Products down in the second reaction. How about that? How do we do? Questions?
I was just wondering, I know it's more likely for the VR to attack the carbon on the right, but could it possibly attack the secondary carbon?
Mechanistically, what's the first step? Protonation of the oxygen. Yeah, we can get to this point. Br minus. At this point, is the reaction going to go SN1 or SN2? SN2, the rule. Okay, there's no tertiary site here. It's secondary, it's not even primary, it's just methyl. No tertiary site, so we go SN2. So that means this is going to attack something by SN2. It can attack this carbon and kick off the oxygen, or it can attack that carbon and kick off the oxygen. Which one is most likely if it's going by SN2? SN2 is largely governed by sterics, least substituted, kick off the leaving group. You wouldn't attack over here. You can, it is secondary. You can attack over there. At least it's not tertiary. But that would be preferred. Sterics largely govern SN2. Much more reactive over here. That's why, okay? And that leads to the bromine binding to the methyl, and then the leaving group was the, what's the name of that alcohol? Common name is isopropanol. IUPAC name? 2-propanol. Common name is isopropanol because it's an isomer of regular propanol or 1-propanol. Okay? Isopropanol, very common name. They sell it at Walmart. They call it rubbing alcohol with like 10 or 20% water with it. Don't drink it. Mess you up. How do we do on these below? Rank this with HI products. I have something here.
Can you walk through one of the mechanisms where the ring gets cleaved?
Let's turn below. Let's go below. Mechanistically, it's the same thing. It's just when the leaving group leaves, it's not really going to leave because it's connected by the ring. All right, let's do this one here. HCl heat. The first step is to protonate, okay? Can we just protonate? Okay, we have Cl minus. The only chemistry that can take place here is this act as a nucleophile somehow. Meaning, or you can take the H back. You're just going to go backwards to the starting. Okay, but it's SN1 or SN2. This is going to act as a nucleophile. All right, what SN1 or SN2 here?
SN2.
I agree because there's no tertiary site available, so we're going to go SN2. So we're going to attack this carbon and kick off the oxygen, or on the right?
The right one
I guess the one on the right.
primary.
One on the right. We attack here, and we kick off the leaving group. And that's going to give chlorine now bonding to this carbon. I'm going to draw it just like this. There's your product. This alcohol was just the leaving group in our SN2. Yeah? No change in stereochemistry here. We didn't do any chemistry of this carbon. So I'm just going to show it just like that. This carbon is not chiral, so there's no stereochemistry there to have to worry about. Jennifer, how does that look?
That looks good. I just attacked the wrong side of the ring because I forgot about like the sterics, part of it. So
SN2.
I had the chlorine on the wrong side. But like I understand like why it just kind of splits the ring like that.
And you did inversion over here when you attacked, right?
Mm-hmm.
Because it would be inverted. You
I did,
just
yeah.
attacked the wrong side. Sterics, SN2, largely governed by sterics. Okay. You can actually react that again with HCl. If you just solve that right there with HCl, what can happen? We can protonate this. And then what can happen here? Well, then Cl minus come in here and kick off the water, yeah? Is that chemistry possible? And if we did that, I'm doing by another SN2, I would get chlorine here, and I would get inversion like this. The methyl's back from here. The methyl's that way, but now it's this way. It's like this, but forward. Chlorine comes in. Methyl's here now forward. That is inversion. We would get this product and we would plus water. Question. It is possible to react our product there with HCl again, because don't alcohols react with HCl to give? Okay. It is possible if we used excess HCl to get all the way to this, yeah? Oxygen served as leaving group twice. The first time it left, really didn't leave the molecule. It just opened up the ring. But then the second time, it really did leave. It left as water, got a second SN2 reaction. The second one came with inversion. Well, the first one came with inversion too, but there's no consequence of stereochemistry. I mean, there is inversion there. But since it's not chiral, we don't have to worry about the consequences of it. Any SN2 is backside attack, and the groups are going to go like this. In that case, it's just two H's going like that. Question?
Can you go over again for the second time, the bold line is inversion and we're not writing it dash?
There's an H here going back. The methyl's coming forward, and the H is going back. But the methyl's also coming this way.
Oh,
It's like this.
okay.
And the chlorine, I brought it in from over here. And when it comes in, this pushes forward. That's the inversion.
It's like the umbrella.
It's like an umbrella like this, or you hold the umbrella like this, it's going, and then it going, boop, going the other way. It's inversion. That's inversion. It's just the chlorine's coming in the plane as opposed to this way. If it was coming this way, the methyl would be forward, but then it moves back to make room for the incoming. It's just the way. Or you can do RS. It's inversion. We looked at it like that in organic chemistry. Okay? I gave you a handout. It was at the bottom of the page of one of the handouts, actually during test 2, ways to make nucleophile carbon bonds. And I showed you different scenarios here. The nucleophile's in the plane here. And the leaving group is in the plane. See, the leaving group's in the plane. The leaving group is not forward or back. If the leaving group was back, this would come in from the front. And you would show it bolded. And so you would go from back dash, and this would become bolded. But we don't have, it's not in the front or back. The leaving group's in the plane, so this comes in the plane. It's that scenario. Why don't you try the others on your own, and you may look at them next time. Reaction below. First off, this is THF, tetrahydrofuran. You can find it on the Wikipedia. Very common solvent. It's a cyclic ether. Very common solvent. By the way, another common ether solvent is diethyl ether. Very common solvent. One problem with both of these, many ethers, is they form peroxides upon standing and aging. Old ether, by the way, this is often just called ether. Anytime you see ether, people are referring to diethyl ether. Will form peroxides. And oxygen will slip in here. And you end up getting peroxide here by some radical chemistry, oxygen from the air. This is unstable, and it can explode. Okay? Old cans of ether in certain conditions. THF will also form peroxides. So that's one thing you have to be careful with them. They're still very common. But with a push to improve solvents and to make solvents greener and safer, there are some alternatives to ether and THF that are coming out, that are becoming more common. Okay. No H plus. There's no H plus. Okay? It's not going to react. How do you make oxygen a better leaving group?
Rotated.
That's the most common way, and that's the way we did on this page, protonated. But if you don't have any H plus, any strong acid, you're not going to protonate, and then it's not going to be able to leave. It's not going to react. No reaction. It will not react with strong nucleophiles. Now, typically, strong nucleophiles are also strong bases. You can't have a strong nucleophile in the presence of H+. Up there, halides. You can have halides in the presence of H+. That's the definition of HBr. H plus Br minus. But you can't have very strong nucleophiles, other types. Ethers are not reactive. They're unreactive. Okay, we got double negatives and all of them. Ethers are not reactive under non-acidic conditions. Ethers are unreactive under neutral conditions or basic conditions. Thus, they make good solvents under strongly basic conditions because they're not going to react under strongly basic conditions. No reactivity. They only react when you have acidic conditions, like above. An exception to this is epoxides. And epoxide is the next handout. And I have another. Blue one today. Epoxides. Epoxides are a special type of ether. The warm-up page here shows an epoxide. We saw how to make epoxides in Organic 1. There's an epoxide here. Epoxide is a cyclic ether, just like THF. But THF is a 5-membered ring. And epoxide is how many in the ring? 3. 1 oxygen and 2 carbons. 3-membered cyclic ether. We call it an epoxide. It's also known as an oxirane. That's actually the IUPAC name. We're not going to look at that. More common name is epoxide. Epoxides are actually formed in the body during some metabolic processes. Synthesis of certain leukotrienes involves generating an epoxide. And in your body, we don't use reagents. How do you make epoxides in the lab? Reaction of what with what? Reaction of an alkene with
Like MCP.
MCPBA, which is a specific example of what? What is MCPBA? It is a peroxide. More specifically, it's a peroxy acid. Okay? Well, your body doesn't use MCPBA, etc. Your body uses certain enzymes, okay? All right. A little warm up there. As you guys who've had other instructors see MCPBA making epoxides? Okay. So you take this alkene, MCPBA, solvents. Okay, I'm showing just different solvents here. This is ether, the next one's THF, common solvents used for many types of reactions. Dichloromethane, we've used that in lab before. All right, you just have to be able to recognize solvents. And most of the time they're inert. By definition, they're inert. Occasionally, the so-called what looks like solvent may react, and we call it a solvolysis reaction. Okay, here we go. We make the epoxide. In this example, this carbon is chiral. We're going to get a racemic mixture of the 2 epoxides. Down here, this is not chiral. Oxide. But if we put a methyl group on, it is chiral, and so we can get a racemic mixture of the 2 enantiomers. Hopefully it looks pretty familiar. All right? You should know the mechanism for that. An electrophilic reaction of alkene. No carbocation actually formed, NAF. Somewhat like making a bromonium ion. All right? Another way to make epoxides. I didn't show this in Organic 1. We can show it now, though. Take an alkene, but it also It starts with an alkene. It's an alternative way from an alkene. You can do a, what's the name of this type of product? Bromohydrin. You can make the bromohydrin. You would get the OH here. Yeah, you should know that chemistry. If you take a bromohydrin, treat it with sodium, you can get the epoxide. Mechanistically, what's going on here? What does sodium do to an alcohol?
Protonate, and then there's like an attack behind the bromine.
No, tell me again.
With the sodium, there's a accompanying negative charge hydrogen that can take the other H.
Yeah, you said a word started with a P.
Deprotonate.
Okay. Did you say deprotonate?
Yes. Deprotonate the oxygen, and those electrons can pick off the bromine.
I didn't hear the D. Sound like you said protonate the oxygen.
No, sir.
We're not going to protonate the oxygen with that. Okay. It's a redox reaction. It's not a traditional acid-base reaction. We can get this. What could this do? Internal SN2 make the three-member ring. Yeah.
Is that still considered an alkoxide, even though there's a bromine on the molecule before?
Yeah, you can still call it. I mean, the alkoxide has a bromine. Okay, so it's another way to make, pretty straightforward, yeah? Maybe you don't have any MCTBA, but you do have some bromine and sodium. Okay, reactions of epoxides. Well, at first, it's just like what we got through with over there with ethers. Okay, just consider it a cyclic ether. We can react with HX, which is acidic conditions, just like the previous page, and we got the same rule. We only do SN2 if we do not have a tertiary site. If we have a tertiary site, we're going to go SN1. Okay? We can still protonate this oxygen. Okay? We do have acid. And then we have Br minus, and so what type of mechanism should we show?
It attacks
SN1 or SN2?
the SN2,
SN2? Where you want to attack?
the left.
The left.
Attack this carbon, not that one. It kicked off the oxygen. What are we going to get? How does that product look? No change in stereochemistry at the carbon. We didn't do any chemistry over there. Just opened it up. No difference from the previous page we were working on. Not the one below. Protonate. What mechanism we're going to do?
Oh, wait, no.
SN1.
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 SN1? So what is SN1?
Leaving group leaves.
It just breaks them.
Uh-huh. See, this ain't gonna wait around for some other molecule to come in here. It can do something on its own. And this is gonna be faster here. The even group leaves. Mechanistically, we're going to get, that just opens up. The other bond is still bolted to oxygen. That becomes trigonal planar, carbocation, trigonal planar, sp2. Now chlorine can attack the carbocation. And we're going to get that like this. Chlorine now bonded here. What's the stereochemistry of this? We got a methyl and a chlorine here, stereochemistry. It's a carbon.
They'll be
Racemic.
Racemic? Okay, you would think racemic because how do you tackle carbocation? Planar, either side, front or back. Okay? But it's not racemic.
Wouldn't the carbocation move to the oxygen to be more stabilized? I mean, wouldn't it be a hydride shift?
Hydride shift is possible.
And that would give an oxygen.
Probably not going to rearrange. It's possible. It's actually, it seems like it should, but it could, it should, it might.
Can you explain why it would if it's a tertiary carbocation?
Yeah, it's tertiary, but tertiary here would be better because we can show resonance. See, this is where the more you know, the more vague things get. The more options you know, it's like, well, what about this? What about that? Hey guys, let's don't learn anything else. Let's just do this, okay? No, you don't want to just do this. That's just memorization, okay? What are the possibilities? Yes. Okay. It ain't gonna happen here. Okay. It's a tough question. It's a tough. Assuming it did not rearrange, what would be the product? Okay, racemic. Well, here's what I wanted to get at. It won't be racemic. Because when the leaving group leaves, it can't just move. It can't go away. It's still right here. And these are electrons. And physics tells us that electrons which have negative charge are going to be attracted to positive. There's still some attraction here. And this is supposed to be not a bond, but some interaction. Okay? There's still some interaction here. I don't know how to draw that any other way. And because there's interaction, the OH is forward. And it's interacting a little bit with the positive. It actually blocks that side a little bit, the top. Actually, it's blocking the top a little bit. And thus, when the nucleophile comes in, it's going to come in from the back. And the nucleophile is actually going to be like that. And by default, it's going to push the methyl the other way. And that's supposed to be a bolded methyl. And there's your product. And it looks like we got inversion. And basically, if you read up here, SN1 with epoxides gives inversion due to significant back bonding. Okay? You ever heard of such? SN1 giving inversion? No, SN1 doesn't typically give inversion, does it? SN1 racemic. But with epoxides, SN1 actually gives inversion. Because when the leaving group leaves, it's still close by. And this interaction, which I'm having a hard time showing so it doesn't look like a dashed bond, okay, not a covalent bond, but this is supposed to be a non-covalent interaction. That non-covalent interaction between the leaving group that left still sort of remains there. And it leads to the chlorine having to come in. How do you show this? It's hard to show this, because if I just did this, that looks like an SN2. And if you're doing SN2, you should be attacking over here, because that's the substitute. So how do you show it? It's hard to show. You can look at what your textbook maybe shows and discuss. The fact that it's SN1 tells us the chlorine is going to end up here, but you get inversion. Think about it. There's your product. Again, the protonated epoxide is a lot like a bromonium ion. Okay, we erased it right here. Yeah? And by the way, if a bromine then came in here, this is where I'll have to tell you that I actually lied to you in organic form. Because in organic 1, we did something like this. This came in and kicked this off. It's exactly what we did. It looks like an SN2. We never called it SN2 because we did this chemistry during test 2. We didn't even know what SN2 was. But that's SN2. But then you have to ask, well, why are you attacking here? Why not instead attack here and kick the bromine off with that carbon if you're doing SN2? Well, back then we just sort of said that you're going to get more positive here. We talked about back bonding. It's more developed here, but it's very analogous to doing that. I don't want to go on here because I want you to think about it first and then ask questions, and we can talk about it some next time as needed. Okay. Now we can use nucleophiles other than halogen. For example, here we have H+. What's going to be the nucleophile here? There's no halogen. What would be the nucleophile? HSO4 minus will never act as a nucleophile with me.
Water.
Water?
Water, yes. Aqueous acid, water here. Can I just protonate the epoxide? Because if we have strong acid, you're going to protonate something. All right? Where does the water attack? Now there's probably going to be questions here. SN1 or SN2? SN2, because there's no tertiary site. We're going to attack here, kick off that. That's going to give boom, boom, boom. The oxygen just got kicked off. Has the H, gets its lone pair back. The water is now bonded here. It's not chiral. We don't just magically lose an H. Something needs to take the H to go neutral. What can take it?
HSO4 negative.
This can take the H, leave the electrons behind. We get final product, which is going to be OH, OH, there. And we reformed what?
H2SO4.
Yes, we reform our catalyst. This is basically formula from here to here. We've added water to the epoxide. H2O has been added to the original molecule, but we used an acid catalyst. Question about any of this?
Is this called a hydration?
Yes, hydration, as we reacted with water. Any questions about this? No? Yes, we hydrated. What type of product did we make?
1,2-butydiol.
Sounds like you probably saw this in organic. One, who said? What type of product did we make?
1-butydiol.
I can't hear.
Diol.
Yeah. What did you say? 1,2-diol?
Yes, sir.
Okay. 1,2. They're next door to each other. What's the general term for next door to each other? Vicinal. Yeah. A vicinal diol. That's important. A diol. You can get a diol by a reaction of an epoxide like this. By hydration of a epoxide. I thought someone was going to ask, how's water able to do an SN2? Water, we said, probably weak. Can water do an SN2? A lot of things are possible with epoxides. All right? Because they're so reactive. Ring strain. All right? Because of ring strain, they'll do reactions where maybe sometimes we said, no, you can't do this. Epoxides, everything's fair game. Okay? A lot of our rules, a lot of our rules change easily if you change something. Never do SN2 on tertiary site? Everybody agree? Okay. Yeah. Boom. Carbon. You never do SN2 here. Right? But guess what? You can change that to silicon, which is just below carbon in the periodic table. You can do standard SN2 chemistry there. All right? So there's a lot of times where we can easily dismiss our sort of rules. And we got a weak nucleophile here doing an SN2. But we got a pretty reactive molecule here. All right? So there's others you can do there. Here, this is aqueous, so there's probably water here. But we also have methanol, another oxygen. And this is catalyst. And so since it's catalyst, all you need is a little teeny micro amount. And so there's only a little teeny water there. You use a lot more methanol. Methanol is going to be your reactant because there's only a very tiny amount of water. Okay, you want to keep this limited. But theoretically, all you need is one molecule of sulfuric acid in this very little bit of water. Methanol is your nucleophile there. Give that one a try. Down here, product here. Think about it. Let's introduce the next. What about under basic conditions? Okay, above was acidic conditions. Hold on, I thought ethers were unreactive under basic conditions. Isn't that what we said on the previous page? THF and alpha ether, good solvents under basic conditions because they're unreactive under basic conditions. But guess what? Epoxides, because of the ring strength, will react under basic conditions. That is, this oxygen, let's see, if we're under basic conditions, can we protonate the oxygen? No, because under basic conditions, you don't have the strong acid. Under basic conditions, there's no acid. But the oxygen will leave. It will leave because of ring strength. I mean, in organic 1, we said oxygen was a poor nucleophile, right? Unless you protonate it. It generally is. But not with epoxides. In epoxides, it will serve as a leaving group. Okay. We're going to introduce strong anions. First example is acetylide anions. Yeah? We saw these in organic 1. How do you make those? From the terminal acetylene or terminal alkyne. React these with a base. Remember these bases, either sodamide, NaNH2, or something like N-butyl lithium. Yeah? All right. Traditional acid-base reactions. Now if we take one of these and put in an epoxide, and this is the simplest epoxide, this will come in. Sounds like that's the bell for end of class.